Good morning, everybody, again. And thank you very much, Stefan, for inviting me to present this MOSES observation system, which we have built up within the last 5 years. As Stefan already mentioned, MOSES is a new observation system which we developed to investigate the interactions of short-term events and the long-term trends or developments in environmental change. And the new thing about it is that the measuring systems are modular and mobile. The systems are designed to capture in a very general way and especially quantify energy, water, nutrient, and also greenhouse gas states and fluxes. Altogether, we invested 30 million euros, and the system is developed as a distributed observing system by 9 Helmholtz centers in the research field Earth and Environment. And the whole initiative is coordinated by the UFZ in Leipzig. We had, as I already mentioned, 5 years to establish this observing system. This implementation period lasted from 2017 till this year. So with the beginning of next year, we are going into regular operation. And the focus of the implementation period were 4 types of events: the more regional, extended weather extremes, heats and droughts, and also hydrological extremes, and on the more global scale, abrupt permafrost thaw events and ocean eddies. And today I will concentrate or focus on these 2 weather extremes. I think the unique feature of MOSES is the combination of event-oriented and at the same cross-compartment observation. And to illustrate how we plan or how we also train to do these event-oriented campaign, this is an example for a heavy rain event and a resulting flood that passes through the river system into the coastal area. What we plan to do, or what we are doing with our instrumentation, is we try to capture the event as it develops. Here, for example, with mobile rain radars, wind lidars, and so on. But we also look at the state of the land surface, mainly in this case at the state of soil moisture. And then if a flood wave develops, we try to follow this wave as it passes through the river into the coastal zone. And what we do, or what is the character of the measuring systems, it's all single measuring systems are transportable. And they are flexible, deployable. They are used in a combination of in situ measurements that capture the event as it passes through, like a rain radar, wind lidars, but also fluvial stations that measure the flow, the water quality as it passes through. We have gravimeters measuring the water budget, and in the coastal zone, there are fixed point stations with multi-parameter sondes and so on. But we also have mobile systems that catch the spatial dynamics, like mobile cosmic ray rovers capturing the soil moisture development. There are drones, planes with different sensors, or ships following the flood waves. And all systems, or the systems, are developed to be interoperable, to really capture cross-compartment processes and interactions. And this is like the table to show or illustrate the observation modules that we have developed. Altogether, there are 11 of them. And what this is supposed to show is they are developed to observe different regions as well as processes like land atmosphere fluxes. The system is set up to cover the marine part, coastal zones, the terrestrial area, and also the atmosphere. And the measuring systems are flexible enough to cover or to observe different kinds of events. And to show what hides behind the model, for example, this is the land atmosphere fluxes model, which consists of 2 cosmic ray rovers to observe or measure soil moisture development during an event. Then for land atmosphere fluxes, we have mobile eddy covariance stations, as well as a greenhouse gas isotope analyzer. And there are drones that measure greenhouse gases in the lower atmosphere up to a few hundred meters. Then these measurements are often combined with the atmospheric chemistry module, which also has an air quality drone that covers the entire boundary layer up to 2,000 meters. Then there are spectrometers and an aerosol lidar going up to 10 kilometers in the atmosphere. And then there are mini balloons going up into the lower stratosphere up to 30 kilometers. So this is how we observe. If we want to evaluate what we measured in our event-oriented observation campaigns along what we call event chains as the event passes through the environment, we need to integrate our event measurements into long-term and large-scale reference systems. Otherwise, we just measured an event, but we cannot assess the impact. So these systems are national and international monitoring programs, also satellite missions. And what we work with in Germany during the implementation phase are mainly the Tirreno and Cosina sites, which are partners and integrated into the international ICOS and eLTER programs. So in our perspective, MOSES is a complementary observation component to the existing observatories. And okay, with this slide, I want to show what we did to set up the logistics, because this is really challenges. And to set up this event-driven observation mode and to train these campaigns, we did what we call test campaigns. And we did several test campaigns of the heat and drought group, starting with larger campaigns in 2019. And we instantly hit the German droughts of the last 2 years, or the last 3 years. We did some device tests. So we had test campaigns with this German drought in 2019 and 2020. And we also had campaigns for hydrological extremes, looking at the formation of convective events like thunderstorms, hail, heavy precipitation, and also the development of floods. And these both campaigns are interlinked with respect to the low flow situation, which we had in those drought summers as well. And this year we did a large campaign in the Swabian Jura, Schwäbische Alb, where we did measurements of 2 groups, because in this area in the summertime we have heavy thunderstorms and floodings, as well as the development of droughts. And just to explain or to show what we did in this test campaigns, here's an example of the drought campaigns, which we did when the drought summer showed that we are having these forest diebacks, or that this was starting to happen at the Tirreno site in the Eifel and at the Harz site, which is also a Tirreno station. And these both sites are forest stands. And as I said before, they are also partners of ICOS and eLTER. We covered what I showed before, the whole vertical transect of looking at the development of soil moisture, land atmosphere fluxes, vegetation stress, and also air quality. Very first results, what did we measure? At the Eifel site, a fresh clear cut was investigated with the mobile MOSES instrumentation, and the clear cut, to no surprise, turned into a permanent carbon source with the calculated emission of about 4.5 tons of carbon per hectare. And this was compared with the Tirreno instrumentation, the stationary instrumentation at a nearby forest. And here the uptake was about in the same amount. Projections of a former clear cut in this area show or indicate that this new clear cut will remain a CO2 source at least for the coming 8 to 10 years. Further measurements showed that in this clear cut, the evapotranspiration was strongly reduced, and this resulted in an increased soil temperature in this clear cut area. On hot and bright days, the soil temperature rose up to 50 degrees, while above the spruce forest, the temperature remained constantly at about 20 degrees. So here, a comprehensive data set was gathered on this heat and drought feedback loop of decreasing evapotranspiration and increasing surface temperatures. Air quality measures showed that at the spruce forest in this area, the isoprene emissions, and isoprene is the most dominant plant emitted biological volatile. This concentration increased substantially, driven by irradiation and temperature. And these isoprene concentrations get transformed into biological aerosols, and this leads to the increased aerosol concentration, which is often observed during heat waves with respect to air quality. Also here, a comprehensive data set was gathered on this process in forests. We also did, as I mentioned before, test campaigns along the Elba River and into the coastal area. In 2018 and 2019, we had historical low flows in the Elbe, and this situation was investigated with respect to the impact on water quality and the reaction of aquatic ecosystems. In 2020, we continued these entire measurements with a focus on nutrient loads and greenhouse gas emissions. And also here, first results show that it is the irradiation and the low water levels that control, or that mainly control, algal blooms. We had in those 2 years algal concentration increasing along this flow path, also causing fish death or dying mortality downstream around the region of Hamburg. At the same time, the nutrient loads decreased along the flow path because all the nutrients were taken up by the growing algae. What was found out is that in this case here, the dissolved phosphate concentration was the limiting factor of algal growth. Once the phosphor was taken up, this algal bloom was stopped because they were just missing their nutrient. So this means, with respect to adaptation measures, reducing the algal loads in rivers should also help to limit algal growth in a changing environment with more heat waves and droughts to appear. And this also has been published already. So to finish my presentation or my talk, where are we standing now? We are at the very end of our implementation phase. We have finished our device tests. We have finished our test campaigns to train this event-oriented logistics and to handle these challenging campaigns. Our data discovery portal, which is a metadata portal, is online since 2020. And we have also established management procedures with respect to the organization of this observation system and also the campaign deployment concepts. So at the beginning of next year, which is quite soon, we are ready for national and international campaigns investigating dynamic events. Yeah, and with that, I would like to finish my talk. I thank you very much for your attention, and I hope I could convene the idea of the Moses observation concept.